All right, welcome back. Good morning, all that usual stuff. We're going to continue right where we left off in a couple minutes, but just want to take my usual 60 seconds or so to kind of summarize what we did at the beginning of 2.5 since we left off halfway in between. We said that there are a few basic graphs you have to memorize. I like to call these sketches, and it's just that you need to memorize how these shapes are, not precise numbers like this goes through 0, 0, then 1, 1, then 2, 4, and 3, 9, and 4, 16. Just the idea that as it grows quicker and quicker and quicker. This U is getting steeper. It's not going to just be like this and be super wide. Now there are ways that it could be wider or narrower that we'll talk about very lightly, but hold that thought. So our x squared, that parabola, is that U-like shape. The x cubed, it's like we took one of its arms and started pointing it down instead. Square root is like we took the x squared, tipped it on its side and cut an arm off. Absolute value is just a v. And then cube root is kind of like the square root, except you get the other leg of it, but it's like the x cubed in that it points in different directions, not just both right. You absolutely have to memorize these shapes, because what we're going to do is just take those shapes and move them left, right, up, down, maybe reflect them, maybe stretch them, but it's not really what we do a lot of in this course, admittedly. Yeah, all right, so we talked about vertical shifts where you have this plus or minus a number outside of the core. We said the core being like the normal x squared or x cubed or square root, absolute value, cube root, whatever. So it looked like example 1. And we said these shifts kind of felt like they made sense because plus is up and minus is down. But then we got into horizontal shifts and things got a little weirder. First of all, that number ends up, the plus or minus ends up being what I call inside the core. So it looks like this or this. So instead of the plus 4 being outside of the absolute value, it's inside. And same with this minus 2. And that's how we can tell it's a horizontal shift. Horizontal changes are inside, vertical changes are outside. And that's always consistent. That's a very awesome thing to remember, because if you try and just remember the reflections independent of the shifts, it feels like you've got 4 things to memorize, whereas at least this kind of condenses it down to 2. But the other issue is that horizontal shifts are backwards, plus is actually left, minus is actually right, and there are logistical numerical reasons for this. I kind of demonstrated that with the checking of, figuring out these points that we went over, and again, all that was done in greater detail last time. And then we got into reflections, and apparently I can't spell outside. That was funny. So this is when you have a negative either in front of the x inside the core or outside of the core function. So either a negative in front of the x if it's inside, or a negative just outside of the core in general. If it's outside, that's a vertical reflection, which means up becomes down, down becomes up. If it's inside, that means it's a horizontal reflection, which means you're swapping left and right. Now, we didn't get any of those examples. I did lay out what those first examples would be. So let's actually do them now. So this is example 3A, and I can squeeze it here. So we're just going to sketch. A, it's going to be f of x equals negative x cubed. Now, I want to show you how you can tell whether this negative is inside or outside. So this would be a different problem. This negative is outside. I'm going to write something quickly, and then I'm going to erase it. So this would be versus f of x equals parentheses negative x, and then the cube still outside. So this one is outside. This one is inside. How can you tell whether it's outside or inside? Use your eyes. So that's the difference between outside and inside. Because that negative we're counting as outside, that means it's a vertical reflection. Anything outside is a vertical reflection. So this is going to reflect vertically. In other words, up becomes down, down becomes up. So here's what I'm going to do. I'm going to draw my axes, my x and y axis, per usual. I'm going to sketch the original x cubed function. I'm going to pretend that that negative isn't there, and I'm going to do this in a dotted image, so this is what I call a ghost image. This is what the normal function would look like. So here's your x cubed. Doing the best I can, blind. Good thing from, there's muscle memory, I suppose. So this right here would be your regular old x cubed. That's a positive x cubed. We're supposed to reflect this vertically. So in other words, this is our mirror. I want to dot it though. That's our mirror, which means everything pointing down will now point up, everything pointing up will now point down. So this bit that's pointing down over here, and this is going to be solid because this is the actual graph, now looks like that. And then the right side, which was pointing up, will now point down. So this right here is the negative x cubed in the blue. The blue is the answer. Once again, the blue ink only is the answer. You do not have to draw these ghost images in my math lab. You probably aren't supposed to. But by hand, I find that it can be helpful, especially when you have multiple reflections and shifts to handle all in one problem, as we will see coming up shortly. So let's do another one. F of x equals, and let's go, and we're going to do two more actually. This will be the square root of negative x. Now that negative counts as being inside. How can you tell it's inside? Again, just use your eyes. It's inside the core part of the function. So that means it's a horizontal reflection. Again, outsides are vertical changes, insides are horizontal. Say it to yourself 50 times, write it 50 times, read it 50 times, apply it 50 times, whatever you have to do. But don't be lazy and not do nothing. It's not going to help you. All right. So again, in black, in a dotted image, I'll show the original ghost, just pretending the negative was not there. Square roots are supposed to look like this. I got a little less dotted there, but just go with it. That's a regular old square root of x. There is no portion on the bottom because it wouldn't be a function. Again, if this part was here, it would fail the vertical line test because it would go through more than once. Okay, so we're going to reflect horizontally, which means this is our mirror. Left becomes right, right becomes left. Don't overthink it. So this thing was just pointing up and right. So now it's just going to be pointing up and left. And again, that was almost perfect. I know it might look like I'm saying this thing is flattening out. Sometimes you can draw these and it just ends up looking very flat. This thing is still going up and right, I'm sorry, up and left forever and ever and ever as we draw it that way. So please understand that that is not flatlining. There are functions that will flatline. We'll study them in another chapter. All right, finally, f of x equals negative square root of negative x. So similar to b, but now with an extra negative in there. So you've got one in and out. You've got this one in and this one out, which means you're going to see both reflections. You're going to reflect it horizontally and vertically. For this problem, the order you do that won't matter. But when we start mixing up reflections and shifts, it will start mattering the order we do some things. And I will get into that then. But for now, I haven't mentioned that yet. So we're just saying it seems like nothing's going to matter the order we do this. So we have a mirror here, and we have a mirror here. So M for mirror, not slope, M for mirror, not slope. So I'm going to do a dotted image for the original one, which is the same as the original for B. So there's our square root of x. And then I'm just going to do two ghost images. So first, and let's choose to do, what do you think? Anybody got an opinion? I'll go outside. That's my opinion. I really do miss being in person class. So we're going to do the outside reflection first. Remember, outsides are vertical reflections. So I'm going to reflect this vertically first, again, just arbitrarily. So again, I'm going to do this reflection first. So this is blue. I'm just going to make them a little thicker looking. So there's the first reflection. So this would be negative square root of x. I haven't accounted for the negative inside. And then I'm going to take this image and reflect the inside. So we're going to do this one second. So everything that's right becomes left, everything that's left becomes right. Well, there is no left, so it's just everything right becomes left. And it's going to erase that part of the arrow because of how I have this clipped, but that's what it would look like if you're not using Word and on the clip point. So this right here is our actual negative square root of negative x. It points down and left. So it almost feels like we just built an odd function. It feels like we had this upper right side and then we reflected it twice to get the other half of an odd function. That's not what this is. Again, there's similar ideas with the whole flipping and mirroring and stuff like that. But we did not just make an odd function. We took one function and just put it somewhere else based on reflections. So again, this thing is not part of the answer. This thing is not part of the answer. Those are ghost images that helped us get our actual answer, which is over there. So again, when you just have shifts, the order you do things in doesn't matter. When you just have reflections, the order you do things doesn't matter. But, oops, let's undo that. That looks awful, doesn't it? There we go. So weird how I hit backspace and it brings the graphs down. Again, I don't understand Word always, especially with this pen. It opens up a whole new world of fun and games, I guess. So the order matters when you have shifts and reflections. The order matters when you have shifts and reflections. One more time, the order matters when you have shifts and reflections. Just shifts, order doesn't matter. Just reflections, the order doesn't matter. But unfortunately, the way we mirror things, if we move right and then mirror, that's different than if we mirror and then move right. And then same for the vertical. So you must do horizontal shifts before reflections, and the vertical shift must be done last. Admittedly, there's a lie in there, and by lie, I just mean it's not a full truth. I'm not going to say what it is, but there is some order that has to be accounted for. And it's really that for horizontal, the shift has to come before the reflection. Again, for the horizontal, the shift must be done before the reflection. But for the vertical, the shift has to be done after the reflection. I know that feels weird, and guess what? It has everything to do with the fact that horizontal shifts are backwards, but vertical shifts are not. That's why this is a little wacky. So the idea here is that the horizontal shift must come first in those pair of things, and the vertical reflection must come first in those pair of things. Now, honestly, there's at least 4 different ways to get this order done and get a correct graph, but there's also probably like 64 ways to do it wrong. So again, that all involves with the fact that just in these 2 things, the horizontal shift has to come first. So you could actually take this horizontal reflection and do it third out of these 4 things. You could go horizontal shift, vertical reflection, vertical shift. That would be okay. You could also take the vertical reflection and you could do this thing first. So you could do the vertical reflection, then the horizontal stuff, shift, then reflection, and then the vertical shift. But it's just too many things to account for. You're going to feel like you're rolling the dice too much. So this is just the order that I highly suggest. And the reason I do that is because you can at least get a semblance of order in that the shifts are going to come first and last. The shifts are first and last, and the reflections are in the middle. You do the shifts first and last. That's an and. That's a terrible looking and, I know. The shifts are first and last. The reflections in the middle. okay? But it has to be horizontal and then vertical, horizontal and then vertical, horizontal, then vertical. So the shifts are first and last. And I mean, you can just remember one of these two things because then the other just fills in the blank. If you remember shifts first and last and horizontal and vertical, this is how I did everything in my brain when I was learning this the first time. The shifts are first and last, but the horizontals have to be done before the verticals. That's how you get this particular order. So again, can I just copy this without everything else? Yes. So again, horizontal shift, horizontal reflection, vertical shift. Now, let's say you panic and it's test time and you go, oh no, I think I got this order jumbled up. What you can do once you get your graph, you will see where that one single point that used to be at the origin now is. It'll be at something like 3,5 or negative 2,7. So if you want to check it, you can plug in the x value to the original function, see what you get, and if it matches your y value, then you're probably okay. Notice I said probably, because you could have this thing pointing in the wrong direction, but at least you know that the shifts are right, so you've got a good chance of being right. All right, so I know that's a lot to keep track of all at once. Let's do a few examples with that all together, and we're on example 4. Sketch. So for A, we got f of x, and we'll just kind of slowly dip our toes into the water. Negative, parentheses, x minus 4, all being squared, then a plus 2. So here's what we should do first. We should first identify all changes going on here, all shifts, all reflections, anything that's changing the core function. What's the core function? Just ignore all the weird negatives, the pluses of a number, the minuses of a number. This is your core function, x squared. So you know the basic shape is going to look like that, but it might be pointing in a different direction, and it's probably not going to be on the origin. So we know that's the basic shape. So now let's write down what all these changes are. Well, let's do the shifts first. For the shifts, inside there's a minus 4. Remember, everything inside is a horizontal change, so that's left or right 4. So it's going to be something 4. Let's see if that's a minus 4, minus. Were the horizontals the regular or the backwards? They were the backwards. So that's not going to be left 4, it's going to be right 4. And you could just draw a little arrow or use the word, whatever. The plus 2 is a vertical shift because it's outside. So that means the plus is up. So it's up 2. Remember, vertical changes are normal, horizontal changes feel backwards. But in addition to these shifts, we also have a negative outside the core. Since that's outside, outside changes are vertical. So there's a vertical reflection, aka a reflection across the x-axis, because that's the mirror. I just need to give myself lots of space for that. So here's what we're going to do. I kind of wish I'd written this a little lower. I wonder if I can do this. I always want to just be able to grab this stuff and move it, but it just doesn't work well. That's okay. No worries. We'll have a nice big graph instead for this one. So you can draw your original core, which was just the x squared. So something like this is our plain old x squared. Now I'm going to do, again, I'm going to go in this order, first, second, third, fourth. That's my order. I've already said there are other orders that work, but for every order that works, there's like 4 that don't work. Yeah, roughly. I'm not doing the statistics in my head right now because it's a really complicated problem to do. So that's our normal x squared. So we said we're going to do the horizontal stuff, then the vertical stuff, and the shifts are first and last. Horizontal stuff, then vertical stuff, where shifts are first and last, which means horizontal shift comes first. There was a horizontal shift of right 4. So write 1, 2, 3, 4. So here's 4. And then we'll draw our phase 2. I'll do it in blue and dotted. Something like this. If the steepness of my parabola changes, just bear with me. I'm doing the best I can. So that was the first step. And I'm not going to keep writing just what that function is. That would be x minus 4 in parentheses squared, but just don't worry about that. Come on, change colors for me, please. Thank you. All right, so in orange, we'll do the second step, which next is the horizontal reflection. So left and right are going to swap. Now, here's what some people will do. They'll say, oh, well, here's your mirror. I'm wrong, by the way. I also did one too many R's, so let's just put a whole bunch of R's. Lots of R's for wrongs, and yes, I know wrong starts with W. I'm just being silly. And they'll say, well, wait a minute. If you mirror here, you get the same shape. Why? That doesn't even do anything. Awesome. Well, you're wrong, because that's not where your mirror goes. Your mirror goes here. This is the mirror. It's always the X or Y axis. M for mirror, not slope. So what that says is this point over here that was at 4, 0, again, this point right here is 4, 0. It's going to reflect all the way over here to negative 4, 0. This is an aspect that's easy to mess up. So it's right there, and then we draw our parabola from that point, just with that basic shape. Again, this is a sketch. So that's the second step. Now I'm going to do the vertical reflection next. Oh, geez. I said something earlier and then I didn't even do it. I said that this is outside, so it's a vertical reflection. I said the x-axis is the mirror, and then I made the y-axis the mirror. So that was an error on my part. I caught myself because I was looking at this negative. I was like, wait, that's outside. What happened? Said it right the first time, got sidetracked, did it wrong. I'll give you a second to erase all that. I even have vertical reflection written right here, and then I did a horizontal. Sorry. I'm going to blame my neighbor mowing his yard, which you probably can't hear, and I'm just having fun again. All right, so we take a deep breath. We did our horizontal shift, so that was right. There is no horizontal reflection this time, so that second step that I did was wrong. Our actual second step should be the vertical reflection that we identified. This is how we catch ourselves from mistakes. It's okay to make mistakes as long as you catch them. So you're going to see a mirror image like we just did in a later problem, sooner than later. But for now, we're reflecting vertically, which means this is our mirror, M for mirror. So this one doesn't have that goofiness. This point was right here, so it's still going to be there. It's just that blue image facing up is now going to face down. Again, if I'm slightly steeper or less steep, don't sweat it. So again, this isn't what I'm saying second step here. I'm saying the second step in our problem was this vertical reflection. That's what I mean by second step. We skipped the possible second step of a horizontal reflection. Now our vertical shift, we said there was a shift of up 2. So this point that used to be at a height of 0 is now going to be at a height of, you guessed it, 2. And in red will be the final image, so we'll do this one solid. So there's our point. And then we just make sure that this is still facing down. I'm going to try and keep about the same steepness. So there is our final answer. I'm just going to write A and S for answer. And there we go. Now, maybe you don't like having all this on your paper to submit for your work. So what you could do is just really quickly sketch the final answer itself. That point is over at 4, 2. So write 4 up 2. Go, and then just sketch your parabola facing down, and there it is. So there's your answer with only the answer on the graph, because that's the only thing you're going to be putting in my math lab in general. So it would be nice to have that on paper as well. But again, this is helpful. Don't just erase all this work. Just go to the side and make another quick one. Again, these are sketches, not super accurate graphs. I'm not having you figure out where this point is and where this point is and where this point is and where this point is. We'll do something like that later. Some of those points were good. I did put one that we didn't actually need. So again, this order just going to keep copy pasting it for the next example so you can see it, but you have got to have this order memorized. Again, or in order that works. Now, I mentioned that how can you check this to see that at least you got this point correct? You plug in the x value, which is 4, and see if you get the y value, which is 2. Again, that point is 4, 2. So if you plug in 4, you should get 2. So if you put a 4 here, 4 minus 4 is 0. 0 squared is 0. Negative 0 is 0. 0 plus 2 is 2. It works. Again, that doesn't prove that this is pointing in the correct way. You'd have to confirm that with your reflections. Oh, there's a vertical reflection, so up should be going down. All right, now I feel pretty good about it. Let's get blue back. All right, so for B, we're going to do f of x equals the absolute value of negative x plus 2, close it, and then do a minus 3. So like the last problem, this one has got 3 things going on. So let's identify what those 3 things are. We have some shifts. The plus 2 and the minus 3 are the shifts. So we have shifts of, the plus 2 is inside, so that's going to be a left or right shift. Since it's plus, that means it's going to be a left shift of 2. The minus 3 outside, it's outside, so that's vertical, which means we're going to go down 3. The vertical shifts are not backwards, the horizontals are. This negative right here in front of the x is inside, so it's a horizontal reflection. HR, abbreviation for horizontal reflection. Those are the 3 things going on. And again, while there are several different orders we can get this done, the order I'm going to choose is horizontals before verticals. Now, I like to do horizontals before verticals because when you plot a coordinate, that's what you should be used to, moving left or right and then up or down. So I just feel like that at least goes with that idea. I try and have rationalizations for everything, a way to memorize things. Just makes it easier on our brains. So horizontal before vertical, that's likened to graphing a point, okay? The shifts are first and last. I mean, that's just going to be pure memorization for most of us. The reflections are in the middle. You might say you reflect on your life in your middle ages. Maybe that'll help you out there. I don't know. Come up with whatever you can to memorize it. I don't have a trick for everything, unfortunately, but I do have lots of tricks up my sleeve. I like to feel. I feel like I have many tricks up my sleeve. Okay, so horizontal shift. So we're going to do the horizontal shift of left to first. Let's get our axes nice and big. Here we go. So left 2 puts us over at negative 2 initially, and we'll do black for the first one. I'm actually going to skip drawing the original shape if you needed to. Here it was before we shifted it left 2. So there was just the absolute value of x, and then this would be the first step. But I'm just going to draw. I'm going to start here this time because I feel like most people understand the basic shape and then to be able to just do that first ghost image without it. So this is our first step. Then our second step is going to be if there's a horizontal reflection, and we're going to get this right this time, I promise, which there was. So we do the horizontal reflection. So this point that was over here at negative 2, 0, when you reflect it across this as our mirror, will now be over here at positive 2, 0. And then you draw your V shape, trying to keep the same steepness. I just realized I didn't put arrows on the ends of the first one. Let me fix that real quick. There we go, boom. So this was our second ghost image. So again, it started at the origin, we moved it left 2, and then we reflected it. Again, this is not the mirror. This is what most people get wrong under horizontal reflections. They'll just keep that point there and say, oh, well, the mirror doesn't even change anything. Oh, yes, it did. Yes, it did. All right, so then we would do the vertical reflection if there was one. That would be if there was a negative outside. If it looked like this, then there would be a vertical reflection, but it's not, so there isn't. So there is no vertical reflection third step. Our third step will actually be the vertical shift, which we said was down 3. So we take this ghost image and we'll make our final one in red. We're going down 1, 2, 3. So here's -3. Here is that point, which some people call a vertex. It can usually be called a vertex, but not always. Depends on your shape. So I'm just trying to make this as best as I can. So that's our answer. And again, if this just gets too jumbled on your own little paper, you can do a side graph and just plot the point 2, -3. And then draw your absolute value facing up. It's facing up because there was no vertical reflection. If there had been a vertical reflection, it would be facing down. All right. Last, but certainly not least, C. We got f of x. Let's do it all, spoiler alerts. Negative square root, -x plus 5, and then a plus 3. Now, I want to point out something here. I don't have to put the core first and the constant last. I don't have to put the x before the constant on the inside of the core. These things can be in all sorts of wacky orders. So I just want to show you that this function, 3 minus the square root of 5 minus x, is the same exact thing, even though I put the 3 first and the square root second, and the 5 in front of the minus x. Because the 3 is still positive, the square root is still negative, the x inside is still negative, the 5 inside is still positive. So you can see arrangements like this, and it can throw some people off because it'll be like, oh, well, what do we do if the 3 is in front? What do we do? What do we do? Well, 5 plus 3 is the same thing as 3 plus 5. Order of additions don't matter. But Mr. Beckner, this is a subtraction. Well, additions of negative means the same thing, so as long as you take its negative with you, then you're golden. All right, so let's list all our shifts, reflections. I like to do my shifts first. The plus 5 is inside, so that's a horizontal shift of 5. Those are backwards, so plus means left 5. The vertical shift, that plus 3 is outside, so that's up 3. They don't go backwards. We have a negative inside and a negative outside, so there is both a horizontal reflection and a vertical reflection. We got all 4 pieces of the puzzle. This is where people make mistakes. The order that you have to do things that I've mentioned several times, and again, variations of this, but this is the one I just like to use. Horizontal, then vertical. Oh yeah, because it feels like coordinates. Horizontal before vertical when you plot a point. Okay, that makes sense. And then you just have to remember the shifts are first and last, or you have to remember reflections are in the middle. So let's do the horizontal shift first. Well, let's plot our ghost image first, actually. Come on, stop being silly. Thank you. So nice big graph. So I'm going to do the horizontal shift first. So what was our core function? The core was a square root. So if you need to do, this is your first ghost image, that's your just regular old square root of x. This one's going to get really busy if I have that up there too, so I'm going to skip that one. I'm just going to go straight to the, let's shift this thing left 4, the horizontal shift. Left 5, excuse me. 3, 4, 5. I don't even know why I said 4. There's not a 4 written on the screen. So that point is now going to be over here at -5. And then we're not doing this. We don't point it left. That would be doing 2 things at once. That would be a horizontal shift and a horizontal reflection. So that's next. Also, it would be wrong. This is the toughest one to do with this tablet. So there's our first change. So that was just moving it left 5. So we did that. Now let's do the horizontal reflection, which means left becomes right and right becomes left. Again, this is not your mirror. It's not just going to do like that. The mirror is the axis. It's the y-axis because we're doing a horizontal reflection. So there is our first mirror. So this point that was at -5, 0 will now be at 5, 0. And this graph that was originally pointing up and right will now point up and left. Too steep at first. Let me come in from the left, actually. This will be easier for me. I would really just love to do this solid like that. Da, 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 da. See, they should actually cross. I know what I can do. There we go. That was better. It's, you know, it's a little too steep, but that's okay. This is good enough. You've got the idea right. Now we're going to do our vertical reflection. So let's go to orange. So we're going to do the vertical reflection next, which means up becomes down, down becomes up. So here is our mirror for this step. So this point will not shift at all. That's one thing to note. When you do this in the right order, you will never end up shifting this point vertically. You're only going to end up shifting it horizontally. And it's just something that you might notice after you do it 100 times. All right, so now let's just point this bad boy down and left as best as I can. There we go. So that was the third phase. And then finally we have our vertical shift. We'll do that last. And that was up 3. So this point that had a height of 0 is now going to have a height of 3. So it's right here. And we'll do this solid. There is our answer. And if that's too much of a jumbled mess, especially if you had the original square root there, dotted of course, then you can just go to the side and say your answer is here. And that point is right 5. So over here 5, 1, 2, 3, 4, and then up 1, 2, 3. But you got to make sure you're pointing that down and left in that normal square root looking shape just reflected. Again, so in terms of when you take this as a test and you show your work, this is a great thing to show, because if your answer is wrong, maybe you had 3 of these 4 steps right, and then I can give you partial credit if you say, hey, Mr. Beckner, check out my work for this. But if all I see is the answer in my math, I don't see any scratch work, you're definitely not getting any partial credit. If all I see on your scratch work is the answer and it's wrong, it's going to be extremely difficult to give you partial credit because I can't see your thought processes. Partial credit is given based on I can visually see your brain working. All right, so the last thing I'm going to mention, and I honestly will not even put this on the test. I think there might be 1 homework problem on this, and it may be 0. I cannot remember off the top of my head. I forgot to check before class because this has changed like every year. Some years we do it, some years we don't. But it's always something that we don't test on because it's not part of the syllabus anymore, but we still like you to see it. You can have vertical stretching or vertical shrinking. The C is just saying it's a number, it's a constant. So that's for a C times your core function. So something like 5x squared, or something like 1/5 x squared. So the 5 and the 1/5 are outside. If it was inside, it would look like this, 5x squared, or 1/5 x squared. These would not be vertical stretches and shrinking. These would be horizontals, and we actually don't even do them at all in here. Just showing you the difference of outside versus inside. So if that number is bigger than 1, then it stretches it. So a stretch, let's say x squared was this graph. Imagine like you're up here and you've got a string attached to your anchors and you pulled that string up. What it's going to make it do is it's going to make it, it feels like it squeezes in horizontally, but we're talking about the effect vertically, so it just makes it grow quicker. Again, this silly little image was me attaching a string to the ends of the arrows and then pulling up, which makes this shape just kind of squeeze together, aka grow steeper. I don't want to leave that there though. So again, the black would be your regular old x squared, the orange would be your 5x squared. Whereas a vertical shrink, it sounds like a psychologist, if this is your normal old x squared, it's like we were pushing down on those arrows instead of pulling it, so it makes it feel wider instead of skinnier. Again, I know I'm using that comparison with horizontal words, but again, it's just the 1/5 makes it grow slower. It's going to grow at 1/5 the speed. So it's going to take 5 times as long to reach the same height as the x squared. Versus in the first scenario, with that 5 there multiplying everything, it will grow 5 times as fast. So if your height was originally a 1, now it's a 5. If your height was originally a 10, now it's a 50. If your height was originally a 30, it's now a 150. So that's the idea of vertical stretching and shrinking. We'll call those 2 examples if you like. Again, not testing on it, so I'm not going to spend an hour discussing it. You have enough information there for the possibly 1 homework problem existing for you. Now, while I say this is not in our syllabus officially anymore, and I'm not going to test you on it, there's a reason I still said it. There's a reason I still did it, and that's because if you're going on to calculus, this is an idea that could come up. I don't know why it's not in our syllabus in a pre-calc course. It should be, which is why I'm teaching it to you, the concept, even though I'm saying because it's not in the syllabus, I can't test on it. So please understand this. It could come up at some point later in your math career, especially if you're going on to calculus sooner than later. All right, so that's 2.5. So that homework will be due in 1 week, which is the 28th. So again, just a quick note, 2.5 homework is due 10/28. So now we're in 2.6, combinations of functions and composite functions, which is just another type of combination of functions. Before we even get to the title of this section, we're going to study the domain of functions, something that I alluded to a while ago, that we'd come back to. We studied domain and range of graphs. We said domain is left and right, range is up and down. We studied domain and ranges of just sets of points. Domain was the x value, ranges was the y values. But we said that we didn't study the domain of functions written out as functions because we were going to save it for later, and here it is. We're not going to do the range of functions. That's a little more complex. So we're just only going to focus on the domain of functions. Now, we're only going to focus on 3 types of functions. There are dozens of other types of functions out there that have domains that you'll see when you get to those types of functions. We'll see another type in chapter 4, exponentials and logarithms, and we can talk about their domains. But for now, we're just going to have this into a 3-case scenario. So you've got to know what case you're dealing with. You have to be able to identify the thing you're looking at. A polynomial is something that looks like f of x equals x to the third minus 5x squared plus 7x plus 2. That's a polynomial. A rational, we need a little more space, is something that looks like x plus 3 over x minus 7. They're fractions with variables top and bottom. Radicals are things that have square roots. So this would be something like the square root of x minus 3. Now we have drawn a few polynomials in here already, whether you knew it or not. We definitely should have known it for the x squareds, but we drew some polynomials when we were talking about increasing, decreasing that kind of look like this. This is how polynomials generally look. They have bends, they're smooth, they don't just all of a sudden take a right angle turn somewhere, and they can have multiples of these hills and valleys. They can have no hills and valleys as well. So that's how polynomials generally look, and we're going to be graphing them a lot more later, but for now, we're just more worried about the function. So the domain of a polynomial, there's literally no thought to this. It's all real numbers. It's everything. 100% of the time, if you are given a polynomial, you can answer it like that. It's everything. Remember, domain is all of the x values that you can jam into this function, that you can plug into the function without causing chaos, without causing the thing to explode. And by explode, I mean things like divide by 0 or spit out imaginary numbers, things like that. there's no problems plugging numbers into a polynomial. You can literally plug in any number you like. Go ahead, take the next 17 years with this function and plug in every single number you can think of, and you'll never have a problem. You might say, well, if I plug in 2.9734214T39, I think I said teeth in there. Ignore that. But if I plug in that number, it's going to be very difficult. Okay, yes, that's true, but you're going to get an answer that is real. You're going to get a number, which means it's fine. It might be ugly, but it's fine. So there's no number you can't plug in here to spit out real numbers. Rationals, we've already talked about their problems. You are not allowed to divide by zero. Dividing by zero makes the world blow up in theory. Yes, supercomputers can do it with weird algorithms and things. We're not supercomputers, ignore that. So what do? We say, all right, well, the denominator might be a little fancier than just an x. If it was x, it means you can't divide by zero. So with denominators of x minus 7, well, you got to figure out when is that thing going to be 0, because it's usually not 0. If I plug in 1, the bottom's not 0. If I plug in 10, the bottom's not 0. If I plug in 0, the bottom is not 0. It would be negative 7. So you have to figure out what number makes the bottom 0, and to do that, you just set the denominator. Now, some people don't use the not symbol here, and I don't care if you don't, as long as you understand that you're finding values that don't work. So that's why I say to set it not equal to 0. So for this particular problem, which we'll do an official one later, but you would set x minus 7 not equal to 0. You'd add 7 to both sides, and you'd see that x is not allowed to be 7. So that means that x can be any number except 7. And you could write that in interval notation, which we will later, but not for this one. I don't want to spoil all the fun yet. All right, so case 3, radicals. This is going to need to go lots of space. Radicals are your square roots, your cube roots, your fourth roots, your fifth roots, whatever. And I've said that in this course, we generally see square roots just because they're more fun, they're more challenging. So the domain of an even indexed radical, so square roots, fourth roots, sixth roots. Notice I didn't say anything about odd roots because the domain of an odd indexed radical is everything. Because you can take the cube roots of positives, you can take the cube roots of negatives. So once again, there's no value of x that you can't plug in and get a legit answer. But square roots, fourth roots, etc., you can only take the square roots of positive numbers. So if this number inside is negative, it would spit out an imaginary number, and we can't graph imaginary numbers with our skills. So we need the inside to be non-negative. So we need that to can't be negative, which is why we set the inside greater than or equal to 0, which makes it so it can't be negative. So it's not just x can't be negative, it's the inside can't be negative. So we basically just ignore the square root and just set the inside bigger than or equal to 0, solve that, and boom, you've got your domain. 2, you're finding the values that don't work. 3, you're finding the values that do work. That's another thing you have to keep organized. It's another thing you need to practice. I know I've said this before, but the 10, 15 to 20 homework problems in my math lab, I do not feel in general that they are enough for you. If you do get an answer right, but you don't feel like you learned it, hit the similar problem. That's the same as, you know, in a traditional homework sense, you'll have like 10 or 12 things back to back that are pretty much the same thing. So my math lab is just taking all those groupings, but only calling it one problem generally. Oh, Mr. Beckner, I don't want to spend the time hitting similar example and actually learning. Well, you're going to have a bad time then. All right, so let's try these out. Example 1, find D. Well, there it is. There's D. I did it. D means domain. For A, we're going to have f of x is equal to 32x to the 9th minus 3.5 x to the 3rd plus pi times x minus 1. Oh my lord, what in the world did I just write? I wrote something ugly and complicated looking for a reason, because this problem is not ugly or complicated, it's simple. You have to look through all the nonsense that, oh, a decimal, ooh, scary. Oh, pi, or an irrational number inside of a polynomial. I hope I don't have to factor that. You don't. All I asked for was the domain. So all you have to do is remember, well, is this a polynomial, a rational, or a radical? And you don't even have to remember the names technically. You just have to remember what goes with what. So here's the way I do things if I'm not going to memorize them by names. All right, fractions have problems because the bottom can't be 0. Square roots have problems because the inside has to be non-negative, so there's no imaginary numbers. This doesn't have any square roots. This doesn't have any fractions with variables in the bottom, because yes, 3.5 is technically a fraction. So there's no fractions with variables in the bottom. There's no square roots, which makes this the easiest case. It means it's a polynomial, which means the domain is all real numbers. Or you could say that double-backed R. But very often they're asking for interval notation, which means negative infinity to infinity. Get used to that interval notation if you haven't already, because that's generally speaking how the answer is. And yes, that was correct. It is a polynomial. So again, absolutely memorizing the names of these things is not a critical skill. It's understanding what wacky feature of these things causes problems for the domain. And the polynomial, the things that look like this, don't have wacky features that cause problems for your x values. For b, we're going to have f of x is equal to 3x plus 5 over 2x minus 7. All right. So I will figure out the name, of course, but again, you could, pun intended, rationalize your way through this by saying, oh, okay, well, there's a x in the bottom. That means this is one of those goofy fractions, and we can't divide by 0. X in the bottom means at some point it could be 0. Ah, so this is that case where we say the bottom can't be 0. So to the side, I take the 2x minus 7 and say this is not allowed to be 0, because if it is, then the function would be 0. I'm sorry, the function's denominator would be 0, and we can't divide by 0, the world implodes. Specifically, this name was a rational. Rational, not just rat, rational. Add 7 to both sides, and you'll get 2x. I'm just doing a colon so I don't have to use too much vertical space. 2x equals 7. Divide both sides by 7 and not equals if you're going to be consistent. Divide both sides by 7 again, by 2 again, excuse me, and you get that x is not allowed to be 7/2. If you don't trust me, plug it in there. The bottom will be 0. You can't divide by 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 0. Don't you dare forget that when you go to calculus. I see you in my calculus class, and I ask you what anything divided by 0 is, and if you say 0, I'll be like, now, I told you in pre-calc 1 not to forget that. I am always honest with what you can forget and what you can't forget. Oops, did that too soon. So x is not allowed to be 7/2. In pre-calculus, this is not an acceptable answer. If this was algebra 1, I can teach this to an algebra 1 student, and then we generally stop here. We use interval notation for lots and lots of things. So we need to write this in interval notation. It's every number except 7/2, so it's almost this, but there's one single solitary number we have to skip over. So we start with negative infinity in a parentheses. And we're going to go up until we hit that 7/2. But we have to skip it. We cannot include 7/2, which means this absolutely needs to be a parentheses. And if you want to see this as a number line, it's just that there is a hole at 7/2. So we're shading everything to its left and everything to its right, which means there's parentheses on that number. So then we have another section, everything to the right of 7/2, which means we need a union, and then it's 7/2 up to infinity. Again, this right here says every number except 7/2. I know it's more annoying than writing it x can't be 7/2, but that's what we're stuck with. We have to put on our fancy pants. C. F of x Am I on time? About 15 minutes, okay. F of x equals the square root of 3x plus 10. All right, so the two goofy cases are fractions and square roots. Well, this doesn't have any fractions, but it does have the square root, which means funny case. Now again, if this is a cube root, it's fine. You can take cube roots of negatives. You've got to think about what causes the chaos. We can't take square roots of negatives and have real numbers. Yes, I know we taught you how to take a square root of negative to plot an I, but we don't graph imaginary numbers in this course. That's a much more advanced concept. You need lots and lots of math to do it, like trigonometry and et cetera, et cetera. All right, so this has got a square root. What's the thing that causes square roots to have issues? So again, this is known as a radical. It's rad, not tubular, not gnarly, radical. So what causes issues with square roots? We can't take a square root of a negative. Oh, that's right. So let's just take the inside and say it's got to be positive or 0. Set it bigger than or equal to 0. And I'm not going to show all the baby algebra here. At this point in our class, subtract 10 on both sides. You'll get 3x has to be bigger than or equal to negative 10. Watch your signs. Divide both sides by 3, and you'll get x is bigger than or equal to negative 10 thirds. That is the domain in old school language, but we need to write it in our interval notation. And our interval notation, please change, thank you. X is bigger than or equal to negative 10 thirds. If you have trouble going straight to the interval notation, remember you can always graph. You can always graph this first. Here's your negative 10 thirds, greater than each shade to the right. That has the or equals, so we bracket it. So there's our domain, negative 10 thirds, comma infinity, parentheses for the infinity, bracket for the negative 10 thirds, because it had the or equal. All right, we got 2 more. I think we got time to finish them. Yeah, we definitely do. F of x equals radicals. There is a potential for them to be negative infinity to infinity. You would have to have just an x squared inside. You couldn't have any, I don't want to say that. If you have a polynomial inside of a radical, it is possible that the domain is everything. It is possible, but that's because the polynomial is completely positive in itself. You would still have to go through this process to determine that. Like if you had something like the square root of x squared plus 5, if you had this, when you go to set the inside bigger than or equal to 0, if you apply your square root property appropriately and everything, you'll find that this thing is always positive, and thus the domain would be negative infinity to infinity. So yes, there can be some weird screwball cases, if you will. I hope that's still G-rated language. If not, I apologize, and I will not say it again if someone's offended. Anyways, yes, what we can do is start having hybrids of these, which is exactly what I was going to do for problem D, but since it was asked, I wanted to go ahead and mention that as well. So yes, the setting polynomials bigger than or equal to 0, going back to a previous concept we learned where we have to do all the test points and all that stuff, that surely can come up. And no, I'm not calling you Shirley. Hopefully I don't get demonetized. I don't actually make any money on YouTube, but I was gonna say hopefully I don't get a copyright claim for making an airplane joke. It'd be silly. All right, back to D. So I don't want to leave this up here for confusion in my notes later. F of x equals for D 5x plus 3. So that question that was asked was an excellent question. I'm not going to do exactly that type of problem, but I will do 2 that are in the same kind of similar concept. The rational ones, by the way, also could potentially have a domain that's everything if the denominator was something like x squared plus 4, once again, if the denominator can just never be positive. We have seen problems like that in chapter 1 where we were finding domains and we said, oh, well, x squared plus 4 can't be factored because it's prime. in real numbers, so the domain's everything. It's always positive. All right, so for D. All right, so you're asking yourselves, is this a fraction, is this a radical, or is this a polynomial? Well, it's a fraction, so the bottom can't be 0. But, uh-oh, it's a radical too. So it is both a fraction and a radical. So guess what that means? We have to account for both parts. We have to say, all right, the radical part says the inside traditionally has to be bigger than or equal to 0, but the fraction part, the rational part, says the bottom can't be 0. Those are the two things going on. Now, here's the problem. The radical is in the bottom. So while we normally, hold on, give me 15 seconds. Sorry about that. Okay, so we have the fraction part because you see a fraction and variables in the bottom. We have the radical because you see a square root, and that's the problematic square root. So the radical part says that it's inside bigger than or equal to 0 traditionally. The rational part says the bottom can't be 0, and the radical's in the bottom. So if we use this, the traditional way, that would say that we could have the square root of 0, which is 0, and the bottom is 0, but that's not allowed. So what we have to do is modify this. So we modify that the inside of the bottom radical must be bigger than 0. There is no or equals. There is no or equals part. Again, that's because the radical was in the bottom. With a radical in the bottom, while you normally say bigger than or equal to 0, because it's in the bottom, you have to cut out the equal to 0 part. In the same way, when we were, I'm trying to relate this back to something else and my mind just went blank. In the same way that when we were trying to use brackets for graphing the fractions, we said anything that came from the bottom, you have to use a parentheses instead of bracket because it's not allowed to be 0. It's the same kind of idea here. All right, so we're going to just set the inside bigger than 0. The inside is the x minus the 8. The top doesn't affect us at all. X minus 8 bigger than 0, not bigger than or equal to. Add 8 to both sides. You get that x is going to have to be bigger than 8. That is our domain. As a number line, here's your 8. Shade to the right forever with a parentheses on the 8. As your interval notation, your answer is going to start at 8, again with a parentheses, not a bracket, and then go up to positive infinity. Now the radical was in the bottom. It didn't have to be in the bottom. Spoilers for E. That changes the swing of things a little bit as well. So you can have a rational and a radical in the same problem. The radical could be in the bottom, it could be in the top. You could actually have both, which is not normal for this course, but you could. All right. Last one of these, and probably the last problem we do today. F of x equals the square root of x minus 3 all over x minus 5. So once again, we have a radical and we have a rational because it's got a fraction and it's got a square root. So both of those issues are going to come up. We're going to have to set the inside traditionally bigger than or equal to 0, and we're also going to have to set the bottom bigger than or equal to 0. Now this time the radical's in the top, so 0 is okay in that. So we're not going to modify the bigger than or equal to 0 part this time. We're going to have to do these as two separate processes because the radical's not in the bottom. So the radical being in the bottom versus in the top changes the game. You have to pay attention to placement. You have to think this through. You have to think about cause and effect. All right, so for the inside being bigger than or equal to 0, that's the x minus 3. So let's set x minus 3, 3 bigger than or equal to 0. Add 3 to both sides, and you get that x has got to be bigger than or equal to 3. Conversely, the bottom's not allowed to be 0, so we take the bottom and say, hey, you can't be 0. So we set the x minus 5 not equal to 0. Add 5 to both sides, and you get x can't be 5. And again, if you're not using the not equal symbol, that's okay, as long as you understand that x can't be 5. So these are two conditions that this problem has to handle. Your x values have to be bigger than 3, but it's also not allowed to be 5. We have to account for both. I am going to highly recommend that you do a graph for this, even though I didn't say to do a graph for the problem. So the two numbers that are important here are the 3 and the 5. So let's just do 0, 1, 2, 3, 4, 5, 6, good enough. So we said that the x has to be bigger than or equal to 3. So that aspect says, here's your 3. You're going to shade to the right of it. And then bigger than or equal means you put a bracket on the 3. Let me do this part in a different color. Let me just do that in blue. So x can't be 5. So here's 5. X can't be 5, so there's a hole there. There's a hole. Which means when you account for both of these things, you can start at 3, you can keep on trucking, keep on trucking, keep on trucking, but because you have to account for everything, the 5 would be a problem. It's not a problem in the top, but it is a problem in the bottom, and you have to account for both of these. So you say, oh, let me take the world's tiniest little hop over the 5, and then pick up steam and go to infinity again. So the interval notation for this one would start at 3, it would go up to 5, parentheses because we're skipping it, union, world's tiniest hop over it, so we pick back up at the 5 on the right side and go to infinity. That is our answer. Now, I know I said we were going to do one more problem, but if you had, say, the square root of in the bottom, let's have the x minus 5 in the bottom still, but let's have that be an x minus 7 in the top this time. So I'm going to do this a lot quicker. From the top, that says x minus 7 has to be bigger than or equal to 0. Add 7 to both sides, so you get that x has to be bigger than or equal to 7. For the bottom, that says x minus 5 can't be 0, so x can't be 5 again. Now, this is the reason I'm doing this. Here's our number line. Now, the only numbers I really need are 5 and 7, so I'll go like 4, 5, 6, 7, 8. Oh, I forgot to do a different color. X can't be 5 in red. So the x is bigger than or equal to 7. That means you start here with the or equals, you put a bracket on it, wrong color, and you shade right forever. The x can't be 5 is just a hole over here at 5. There's our hole this time. But notice the hole isn't in the shaded region. So when you write your answer in interval notation, you don't even have to account for it. So there's no effect in the answer. It's just going to be 7 to infinity. That's our answer for that one. Versus the last one where we had to skip over the hole because the hole was inside of that window. Again, I'm not asking you to memorize 40 or 50 different scenarios. I'm asking you to think cause, effect. put pieces of a puzzle together, not just, oh, rationals are fractions, radicals are square roots. And all right, so square roots set the inside bigger than or equal to 0. Why? Why are we doing that? Because blatant memorization isn't going to help those synapses in your brains connect. I know I probably get 1 or 2 less examples done than other teachers because I rant a lot, but my rants are usually trying to connect all the pieces as well as reminding us the importance of moving forward and remembering things. Okay, so with only like 2 minutes left, we'll go ahead and call it a day there, but you can see the next thing that we're going to be doing. We're going to add, subtract, multiply, divide, and eventually compose 2 different functions. So if I give you an f of x and a g of x, I'd say we're going to learn how to add, subtract, multiply, and divide them, but honestly, you should already know how to do all those things. It's just going to be using that funky notation, and that goes away in like 3 seconds. So that will be quick, except for the composing, but we'll do that next time. So 2.6 is not due in a week. We'll finish it next class on Monday, and it'll be due a week after that. But again, 2.5 is due a week from today, which is the 28th. And I believe I'll have a test date for you next time. So just hold on to that for now. Email me if you have any questions. Have a good day. Take care, everybody.